So we have been enqueuing things, and then when we said dequeue, what we have removed? We have removed A, right? So the first person who comes is the one that we are going to call, right? So A has been waiting the longest, and when we say dequeue, so we remove A, and B and C are remaining. And then when we say dequeue again, we remove B because B comes before C, and then C remains. And then there's another guy called D who came, and D is behind C. And then we call C, dequeue, remove it from the queue, and we are left by D. Dequeue further, so we call further next, and D comes to us, and the queue is empty. We call further next, there's nobody, error, and that's why we have an error here. So dequeuing for when we have nobody, actually there should be some parentheses here. So dequeuing when the queue is empty is obviously going to give you an error. So this is what a queue, how it works. So we see the semantics. So a queue is first in, first out, FIFO. First in, first out. So whoever comes first is going to leave first. The one that is enqueued first is going to be dequeued first. Okay. So a stack a stack is LIFO. This one is FIFO. A stack has only one index, which is the top, because the bottom is fixed, it doesn't move. But the queue, both of them move, so it has a front and a back. Conventionally, the queue is horizontal. The operations that we have are in queue, and we have seen what it does. Dequeue, we have seen what it does. Peak, very similar to the stack. Is empty, is full, size, they are also similar to stack. So queue also has a maximum size and has a current size. So maximum size like 50, and the current size, for example, is 5 if the queue contains 5 elements. If we want to implement the queue as an array, so we are going to define the array, which is the queue here. I'm saying the implementation is circular to save space. I'll return to this in a bit. But now let's just look at the queue as an array. It's an array from 0 to max minus 1. The queue of, so F is the front index, B is the back index. Q of F is the element at the front of the queue, and Q of B is the element at the back of the queue. In QX adds an element. Okay, let's talk about this by drawing, and then. So let's say max size of, so let's say max size of the queue is 9. So this is how big the queue can grow. And so far, let's say we have the element A and B, and now we want to say in QC. Now first, can you tell me what is the value of F? So this is the Q. So what is F? F equals what? F is the front index. Okay, we said we have indices and we have elements. F is 0, and B, Q of F, and Q of B is B. So this is small b and this is big B. So in order to say in QC, how do we program that? Huh? We put it behind B, and in terms of programming, how do we do that? Yeah. Yes. What's your question?
When we take then A equals 0 or 1.
I did not hear you well.
A equals 0 or 1.
A equals 0? Okay, what I said was F equals 0 and B equals 1 and Q of A equals A. I mean, A is just A. A is just an element. Was it because of my bad writing? Yes? Okay. So, in QC, yeah, how do we program that? Increasing back, so back plus plus. So back now, instead of pointing here now, is pointing here, right? So, and then Q of back equals C. And this gives us C here, right? So this is how do we do in Q. We increase the back, and yeah, we increase the back, and then what? And then we do the assignment. Now DQ. How do we do DQ? Okay, so we have some temporary variable and we store A inside it, and then so after removing A, what is the front of the Q? Okay, so after that we do F plus plus, right? And then Q of F, sorry, that's it. And then return F plus plus, and then return what? T. Okay, so this is our temporary variable. We stored A inside it, and then F plus plus, and then we return T. Okay. Well, obviously we could have returned. Yeah, no, we return T. That's how it should be. That's the code though, which makes more sense. So, do you have a question? Because we are going now to look at more complicated cases. B. So F was here, and now it's going to look here. And that's B here. Okay. Now let's look at more complicated examples. Yeah.
Don't mind, give us 5 minutes to chill out.
Huh?
Give us, if you don't mind, 5 minutes to chill out.
5 minutes?
Yeah, chill out.
I'm sure you can chill out in 3 minutes.
Okay, it's okay.
Okay, so I see you at 11:06. x equals 9. Okay, time's up. So, let's say we have been adding elements to our queue, and we have added elements from A to I, A, B, C, D, E, F, G, H, I. And now we want to add a new element, so what happens? Now we want to enqueue J, what happens? In this case we cannot, it's an array, it's a static array, okay? So we cannot add J, so basically we are going to say it is full, okay? The queue is full, we cannot add any element. Now, I want to dequeue, so what happens when I dequeue? Which is? So we have removed A. Now, I want to... So what is the front now? So that's the front element. So front element is B, and that's the back element. Now I want to enqueue. I still insist. I need to enqueue J. Shift. Okay, so shifting is one way, but shifting is expensive. Okay, so what we can do is we can go back from here to here and put J here. And this will be the new value of back. So this is what we call a circular queue. It's basically the queue is like that. Yeah, exactly. You return again to the beginning of the queue if you cannot add at the end of the queue. Okay. Now I want to dequeue. So what's the new shape of the queue? The front now is C, right? Now I want to dequeue Now I want to inq ij, hey, whatever is after eg k. So what's after k? Sorry, I want to inq k. So k becomes here, right? K becomes here, right? And b becomes that, right? Now I want to dq. I 1 2 1 2 3 4 5 6. I want to make dq 7 times. So this is the first time, second time, third, fourth, fifth, sixth. Okay, 6 times. So f becomes that one, right? So I have made dq 6 times, and now the front of the q is I, the back of the q is k. Now I want to make dq another time. What happens? So I is removed, and what's the front now? That's j, right? So this is what is a circular Q. Okay, so circular Q, we can add elements at the end if there is space at the front. Okay, and we can also remove elements and go to the start. And actually, this is what I say in the slides. So I already explained these things here. So in Q, increment by 1, and go back to index 0. Okay, and DQ also very similar. So Q so far, we have talked about circular Q. The only new thing about circular Q that we need to care about is actually the size. The size of the circular Q is going to be another issue. Let me review it very quickly. Because when the Q is not circular, the size is very easy to compute. So that's our Q. We add elements A, B, C, D, for example. This is front and this is back. And in order to compute the size, this is going to be B minus F plus 1. So that's 0, 1, 2, 3, 4, 5, 6, 7. So B minus F plus 1 is going to give me 3 minus 0 plus 1, 4. So the size of this Q is 4. Okay? When I remove A, and front is this cell here, then the size is going to be 3. Okay, so again 3 minus 1 plus 1, which is 3. So this is when back is here and front is here. However, when the Q becomes circular, we end up at situations which look like that. That's front. That's front. And that's back. Or is it? Front. I'm just trying to check if I got them in the right order. FB. Can this happen actually? No? So Okay, I'm unable to imagine. Let me just create a hypothetical situation. So we have elements here. This is F front, blah blah blah, and this is, so we add element. This is front. This is back. Add another element. Add another element. This becomes back. Remove elements. Okay, so we can have B and A. So A, B. So we can have the back here and the front here. X, Y. Okay, because the Q is circular, we can end up in a situation like that. The front is pointing here and the back is pointing here. So we have been dequeuing until the front is pointing to this position, and we have been adding in queuing here and circularly move to the other place until B is here, right? So this situation is very possible. However, if we apply this rule here now, it doesn't work. Okay, the size of the Q in this case is exactly 4. Now B is 1, minus F is 6, plus 1, that's going to give me what? Minus 4. But the size of the Q is really 4. It's not minus 4. So, in order to compute the size of the Q, what we do is actually, we compute, because the size of the Q here is the size of that part plus the size of this part, right? Now, the size of this part is easy to compute. It's B minus 0 plus 1. So it's B plus 1. And this one is also easy, which is max minus 1. This is the last one, is max minus 1. Max minus 1, which is the index here, minus F plus 1. Minus 1 and plus 1, they cancel out, and we get max minus F. So the size of the Q in this case is max minus F plus B plus 1. Okay? Because it's circular. So in the other case, it's equal to that. In this case, it's equal to max minus F plus B plus 1. The two rules can be combined using a modulus operation, which you can read about in the textbook. So here I'm just trying to explain to you without using the modulus operator. If the Q if this is the Q, if the front is less than or equal to the back, then it's B minus F plus 1. If we find that the back is less than the front, which is this case, so this is full, this is full, this is full, and everything here is empty in the middle, then it's less than the front, which is this case. So this is full, this is full, this is full, and everything here is empty in the middle, then it's this plus that. And we know that this is max minus F plus B plus 1. Okay? So, if this is the case, that's the size. If that's the case, that's the size. Or you can use a modulus operator to combine both of them in one equation. Okay, so this is a note on the size of the Q when it is circular. Now, where am I in the lecture? Okay, almost finished. 11:16. So we have seen arrays and we have seen linked lists, and these are called concrete data structures. They are concrete basically because they are simple, and we see how we can implement them in main memory. Okay, they are provided in the computer language. So array, there is something called array. In some languages like Ada, like Java, there is the linked list for linked lists, or we can implement it using pointers. Okay, but still they are called concrete data structures because when we deal with them, we know how they are represented in main memory. We can see them. Now there are abstract data types, which like the stack and queue. They are data structures. They come with a set of operations. Like when we talked about the stack, we said it's a container. We can add an element to it, and we can remove elements from it. And the computer uses it, or the CPU or operating system uses it to organize procedure calls, etc. So we don't need to know how the stack is represented in main memory in order to understand it. That's why it's an abstract data type. It's just abstract. We don't need to understand it at the low level. So one is concrete. We can see it working in main memory, addresses and all. And the other one is abstract. It's a data structure that comes with a set of operations that define how this data structure is useful. Okay? So we just use abstract definitions in order to understand it. And then we have seen how we can implement the stacks and queues using the abstract data types that we have seen. So array, linked list, concrete data structures, we know we can see them working in main memory in order to make use of them. Abstract data types, we don't need to see how they are implemented in main memory in order to make use of them. We just need to understand their operations. And then abstract data types, we program them using concrete data structures. So here I'm giving an example difference between integer data structure and an abstract data type. Okay, so what I'm saying here is, I'm not sure if you have done this already in computer organization or something, like how an integer is represented in main memory, like sign and magnitude, 2 one's complement, 2's complement. Have you done that? Okay, it's not a major issue anyway. An integer, obviously, you are not going to store the number 5 or the number 7 inside the register or inside the memory location. It is going to be in binary. Now, how are you going to represent 5? How are you going to represent minus 5? Are you going to use an extra bit, or are you going just to invert the digits? I mean, invert the ones into zeros and the zeros into ones. So all these things are how to represent an integer at the memory level. This is like the concrete part. Now the abstract part of it is, this is an integer. We don't care about it. I'm programming with an integer in Java. I can add it. I can multiply it. That's it. This is all I care about. So this is like the abstract data type integer. Okay. So concrete is when we look at the thing and see how it's really implemented. Abstract is when we don't really know and we don't really care about how it's implemented, but we have operations to make use of it. So integer, we can add it, we can multiply, we can divide. That's all we care about. So abstract and concrete. It's easier to visualize in the case of arrays and linked lists and stacks and queues. Okay. So, as a summary, we have seen these things. And for further reading, you can read these sections from the 5th edition. Now, do you have any questions?
No, thank you.
Right. Now you can chill out. Yeah, go ahead. Say it again. Yeah, lecture 1, 2, and 3. You're lucky because we did not do any sorting.
Perfect.
How about the question?
Your luck is going to run out when you know the questions are going to be harder, of course.
Please, come on.
No, I'm joking. The questions will be normal. What do you mean by what's your question about the questions? You had a question, you said something, no? Okay, I just imagined.
The time of the question, like
It's usually 1 hour. The type. Okay, the type of the questions, you can see the previous midterms. I usually don't have any true or false, no. If I feel extremely generous, I might, but usually I don't feel extremely generous. I really can't say anymore. Just look at the previous midterms and maybe they give you an impression.